Day 53, Honors Physics, Rotational and Translational Equilibrium, Torque, problem number 30. Here's a good problem. It's a diving board. And this red line represents the diving board and all forces acting on the diving board. It's kind of nice because everything's perpendicular, so we have the sine of 90 in all four cases here for the forces perpendicular to the board. So let's draw the free body, all the forces, as much as we know. Excuse me. So the person standing on the end over here is 80 kilograms, so they're exerting an 800 Newton force straight down on the end of the board. The board itself weighs 300 newtons. I think it says that. Oh, it's 30 kilograms, so we're using 30 times 10 to get the 300 Newton weight of the board. And we put that in the center because we are assuming the board is uniform board. So now looking at the numbers given, well, let's back up a little bit. Here's the tricky part of this problem. The force is exerted by the two supporting posts and the directions of those. So this might be the hardest part of the problem. Think about this. Over here, this force right here, F1, I've aimed it or pointed it down because that post is pulling down on the board. How do I know that? Well, you got to think about this a little bit. For example, if I were to, there's a bolt here that holds this post on. If I were to cut the bolt over here, or cut that support, while this bolt is free to turn, which way would the diving board, if I hold this point fixed, like it's my point A of rotation for my torque, which I'll do here in a few minutes, which way would the board turn if I let the other post loose from its connection on the left post there? Well, that left end of the board would go up because the right end of the board would go down due to the swimmer pushing down with a clockwise torque. The board over here, or the post over here, is holding that board down. So it's got to be pulling down on the board to keep it down, in other words, keeping it from going up. So on the left-hand post, that force is down. And the weight of the board is down. The swimmer's force is down. There has to be at least one upward force, and there's only one force left. And that force is F2. And you can even think about this. The swimmer is pushing down. This board is holding it down, pulling down on that end. So this, just think about it, I guess from a common sense standpoint, this board has to be, or this post has to be pushing up, holding everything up. Like I said, there has to be one force up. This force right here will be the sum of these forces. That force, and this force, once we have some things figured out here in a few minutes. So what I did is I took point A as my reference point to calculate torque, which then takes this force out of the equation for torque calculation because it has no distance from point A. So with reference to point A, over here on the right-hand side then, finding the torques, I have the clockwise torque, which will be this force pushing down at a distance of 75. By the way, how did I figure out the 75 there for the distance? Well, the whole board is 3.5 meters long, and this is dead center. So 3.5 meters is 350 centimeters. Half of 350 centimeters is 175 centimeters. So it's 175 centimeters this half of the board. That's why I got the 175 there. And 175 centimeters this half of the board. And it's given that this is 50 centimeters and 50 centimeters. That's 100 centimeters. Plus the 75, not to scale. So the total distance here is 175 centimeters. I'm just using the geometry of the problem to figure out these distances, 75, 175, and the givens 50 and 50. All right, so once again, from point A, I have my 300 newtons times its distance, 75. It's trying to make the whole thing rotate clockwise with reference to point A. So 300 times 75, plus the 800 times its distance from point A. Once again, measure every distance from your reference point, not from other forces, but from the reference point. That's 250 centimeters from point A. That's 800 times 250 equals the counterclockwise producing torque. This guy, F1, is trying to make the whole thing revolve or rotate counterclockwise with respect to point A at a distance of 50 centimeters. So it's that unknown force times 50 centimeters. The only unknown there is F sub 1. Calculate F sub 1. That's half of what we're looking for. And then I also know, like I said earlier, once we know F sub 1, I got that from the rotational torque equilibrium. Then I also know from translational equilibrium that this plus this must equal this, because there's one upward force that must balance out the three downward forces. Here's my expression there. Bottom line, you'll just take your answer from there and plug it in there, and you'll get f sub 2. All right, have fun with that one.